So each of these is calculated by changing W00 a little bit. And this is then the change in L divided by that little bit. And then of course for all weight values. Done. Then this should be the gradient matrix. Gradient W of L. So this is the original, and then for each element running over I and j, add a little bit, epsilon small, and I recalculate the loss, and then we print the difference in the loss divided by that epsilon. That is of course not the way you should do it. Hello, Status Videos. But it gives me the an approximation of the numerical values that I should find. Kind of can copy this now. And you can continue with the theory. Theory that I wrote as a comment. A long time ago in another universe. Oh, there it is. So it was this universe. So the W is a Q here because we are talking about the second layer. It uses Q as the weight matrix. So I have to change all these W's here and Q's. What am I doing? Oh, that's still correct. Yep. 1 0 here. Zero 1. 1 1. 0 2. And 1 2. Approximation sign, okay. No, I made so all the others, 3 of them. So this thing here, the gradient, I don't know, how do I even pronounce that? Nabla sub QL, yeah, but that's not what I... Fuck this. No. No. Yeah. But did I make it up, or is it really true? Okay, I'm gonna pronounce it like that anyway. It's the gradient of L with respect to Q. And using the chain rule, we can write that as this one, right? So you can express that as the gradient of L with respect to O multiplied by gradient of O with respect to F multiplied by the gradient of F with respect to Q. And I have all those because that one that's this one. Or do I have it? Ah, yeah, here it is, sorry. This one. I have this one, and we have this one, and I have this one. Yep, and then I'm saying here that they must be multiplied in this order. Let's just repeat it. Okay, here we have use J because I think it should be a row vector. So that times this one well, I just multiply it outward. I mean, who knows? Oops. I need a other key. And then eventually multiplied by this one, which is a three-dimensional thing, by the way. So going from here to there is going deeper into the monitor. And so this is the from here to there is a new column, and from here to there is a new row. From here to there is deeper into the monitor. So this is 1, 2, 3 deep, and again 3 deep, too wide and too high. Hello, Gabriel. Yeah. Let me put it like this, because otherwise it becomes too much. I mean, who cares about the notation? We just make it up as we go. Well, it's only too high now. Some artistic shifting. Oh, I should have filled in the values. I'm still missing that. Oops. Empty line. And then that. And you get Z0. What is Z0? Well, I have that here, I think. Z was Z0. Is this, yeah? Yeah, I think so. And then Z1 is the one below that. Z1, Z1, Z1. Yeah. choose two spaces like I did that before, above. Kind of. Okay, now we get three zeros here, man. I think I should continue with this one. Let's put it a lot further. Or maybe not. I don't know, just repeat the same thing. Yeah, here I put an empty line between the rows. We should do that here as well. It's more like that. Replace. Nope, this does not want to do that. So I'll just insert it and then delete the space. And then I get 3 more zeros here. I think I should just use the numbers here. So Z0 is that one. Z1 is that one. And same thing here. Yeah, well, it's not going to fit on my monitor. Just keep them shifted a bit, I think. How about this? No, too vague. Want it to be like that, the middle zero, the first comma. And then here we have, well, if I would do it like that, it doesn't fit. No. Now the big question is this the case? And if so, How the hell am I supposed to do that calculation then? So this is 1x2, and this is 2x2, and this is 2x3. So we are going to end up with 2x3. Or it's the same as 2x3, and that should be equal to the shape of W or Q. And that is 2x3, so that seems to be correct. Should get this the correct shape at least. How do we do this calculation? I'm just going to guess that is equal to so I should get to 2x3. So 2 high and then 3 wide. I think I should be able to do this with my program. So maybe I should calculate this first with the program instead of putting 20 minutes into trying to do it manually. Now I have my program anyway. So we want to calculate this. Let's say, well, the first thing is a row vector. I'll just start at the beginning. That is a row vector. That is a vector, but not really. My vectors are vertical. Let's make it a matrix. And I'm going to call this A because it's the first one. And then we have to pass the shape, and then that is then 1, 2. One row and 2 columns. Yeah, that would be this one. And then you have to initialize it as follows. Row is always 0, and then of course column is 0. Is this value. And A 0, 1 is that value. Then you get a matrix, and this time it's a matrix with a shape of 2, 2. And B0, 0 is that value, and B1, 1 is that value, and the other others are still 0. They are initialized at 0, so why would I type it? Same thing with this actually. This is a tensor. Well, let's see. With a shape of number of rows 2, number of columns 2, depth 3. And C. Now this is of course 0, 0, 0, 0, 0, 0. 3 zeros equals that value. And C 0, 0, 1 deeper is that value. And even 1 deeper is 1. And then repeat that for a row down and a column down. So that is, just copy this. Replace these with 1s. And now we can multiply this. Let's call this result equals are we going for it? What was it called? Contract. Now, let's say we multiply these two first. Why not? So that would be B, C, and then you have to give two integer values. The integer values that you have to give is the things that we have to combine. So that is a 0 or a 1 here. And here it can only be, can only be 0 or 1, or 2, but that would be 3, that is not allowed. So we have four possibilities. And I have no clue how to combine them. Well, I should have a clue, of course. Well, I'm just going to try all of them. Ha ha ha. We begin with 0, 0. It's only 4 possibilities. And that gives then the multiplication of these two. And now we multiply that. Maybe not smart. I should start with multiplying these two, because then at least I know how. Okay, we start with multiplying A with B. And then of course we need to combine the columns. Yeah, so that's the 1 here, that is column. 0 is the rows and 1 is the columns, with the row here, so the other way. So that's a 0 then here, yeah. And that would, this is that thing times that thing. Or is it? I mean, what does that give me? I don't even know. Let's just print it. Just A times B. What? Cannot do that. Oh, tensor is a template. I have to tell it that it is 3. That's again a row vector. No, okay. Why not? and then we multiply that result as first one with C, and now we have 4 possibilities. I'm just going to do 0, 0. Actually don't, because now it's always 0. No, it must be 1, of course. Combining these, yeah, it must be 1 again. So it's a row vector, and we want to do the same thing here. So we run over the columns. And this then must be 0 or 1. I don't know which one. Yeah, it's really chicky wavy. Chicken wave. Wave the chicken. Kind of look like the same values, yeah? Minus 0.0226. Minus 0.0226. Here we have 0.0821, 0.0821, 67 even. It's exactly the same. Yeah, and this value is there. This value 2274 is there. They're all there. It's exactly right. So the first guess was the correct one, but more importantly, it worked at all. Of course, I'm still going to try what happens if I use the 1. That was the only other possibility. And now the values look like not random, but exactly the same again. What the hell is going on? Those are the exact same values. Apparently it doesn't matter. Seriously? Probably seriously. Yeah, that's exactly the same result. So now I still don't know. What the hell, man? Why? What's going on here? What's going on? Okay, if I try 2, then we should get an assert. At least give me that. Yeah, assert. Okay, so now I still have to think to know if it is 0 or 1. But the result is the same. And let's write this out in the correct way. I think that the inner... Why the hell is it putting square brackets around the scalar? Oh, because it's a depth 1. Interesting. The innermost thing is the first one, which is rows. So we have 1 row, and then 2 columns, and then a depth of 3. And the other one was exactly the same, right? Even that doesn't change. Man, it's almost scary. Scary precise. really weird. Okay, now how was this calculated? Wouldn't that be nice, you know? So using backpropagation, there's probably a voorkeur in English for from which side we start. A preference, yeah, from which side we start. I think the preference is starting at the front, right? Going back. OFQ, yeah. So, yeah, so multiplying it in that order isn't that bad. So I think that if we multiply this with that, we just get that. Oops, what the hell? I'll do. Where's my cursor? This value times that value plus this value times 0. It's that value. Followed by, again, this value times 0 plus that value times this value. Need an X. It's about 4 minutes. Yeah, now you have to calculate this. Sure, that is. Yeah, I'm gonna do one by calculator here. 0.7413 65073. times 0.1868156 0.138499 or 985. And the other one, I'll believe it is matches with calculating just A and B. One 138,499. Yep. No, that's the other one. Now you would say you have to just calculate it as if it is a normal matrix, except that it contains vectors. So that would be this times that vector plus something else times 0. So I might as well ignore that. Then where's my 3? Oh, this is the 3. Then if I do a row column, that would be 0, 1 and not 0, 0. And the reason that if I use 0, 0, you get exactly the same thing is because this thing is symmetrical in rows and columns. If you take the transpose of this, it's just the same thing. So that doesn't really matter. But it kind of makes sense, I guess, to just pretend that this is a single thing and then combine this row with this column. In other words, 1 here and 0 there, yeah? And that's, I think, what I have also at the moment. Yeah, I used 1, 0. So we work that out. We get again a row vector existing of that times that plus that times that, but that's 0. No, I'm not going to type that one. And then we get this one times that. Now, how many shall we do? One more, and it becomes a 9. It's a lot of work, but okay. Minus 0.0380982 times 0.5993269992 is minus 0.0226025. Go to 1 0 because that's good. Comma. And then again, minus 0.0380982 times 0.59688438. It's minus 274002, comma, that thing times 1. So that's 1, that's a row, number of columns is 2, and then the depth is 3. So the columns, this is the first column, that's the second column. That becomes a rows. So this is now the first row. And the depth becomes columns. So yeah, it's just that thing on the first row. And that thing on the second row. But we lose the comma. And we get different braces. It's now too high, 2 rows. Which should be exactly equal to what we predicted. Empirically, yeah. That should be equal to that. Well, close enough. And that should be equal to that. Also close enough. And yeah, also right. That's exact. Yeah, well, what I'm not happy about here, my microphone's turned away. What I'm not happy about here is that that we have temporarily a 2 times 2 times 3 tensor. Seems like a memory waste, half of it is zeros. But, yeah. Not only that, this is a duplicate of that, so it's even a fourfold memory waste and therefore speed waste, if you ask me. It seems more sense to just go straight to that times this vector and that make that produce this row, and then that value times the same vector, I'll let that produce this row. We have a lot of inputs, this might be long, and these two stand for probably also something that can be large, so it maybe doesn't really matter. I think we can go straight from two vectors to this matrix by multiplying. To multiply it the right way, you would get an expansion instead of a contraction. That was called the tensor multiplication, I think. So that should be possible. And then all we need is these two vectors. Well, this one comes from a normal, a vector with the, if you multiply a vector with the matrix, and then you do, yeah, you combine that again with another vector to get this matrix here. I wonder if TensorFlow can do that. Also, these were just the inputs, right? These values. At least the inputs of the inputs of the second layer, I think, yeah. So I'll highlight that one. That comes from here. This is the Z, it's the activation of the previous layer. So that is the input of the second layer. And then this is That's those two things combined. Now this is a diagonal matrix. It will also lead to an optimization, I would say. This number is simply that number times that number. No need to start multiplying with 0 and then adding that. So where does this number come from again? That is unknown. Really? First time that shows up is here. It is already a derivative. Huh? Oh, it's a difference. Difference between the output and the target. And then that is the other one, of course. Yeah, so these are this vector is the difference between output and target. This is the input of the current layer with a 1 added. And this value comes from would be that value. Yeah. That comes from this. Okay, that's the value of the derivative of the activation function at that point. Or we can get that from this value, which is the output itself. So we use this output both to get the derivative of the activation function as well as the difference. So by subtracting the target from it. When I want to do the layer before this layer, then I'm having a problem, I think, that I don't know what the target is. I don't know how that works. I mean, this is the last layer, so I do have my target output. But it's an open question for me what to do with the layer before that. I probably should understand that first before continuing. Let's continue with the example. Web page. So backwards pass. We're just looking at a single weight, and then we talk about, we want to know what is the partial derivative of the loss function relative to that one weight, which is then also separated into, with the chain rule, 3 parts which are calculated. We did that as well, so So that gives them this value here, 0.082167. This one. It's kind of surprising that I do not get the exact same value. I get 7.3. There's a 0 here. Why would that be? Can we track back the intermediate values as well? Should be able to, I guess. So there is a multiplication here. This number comes from, well, I lied. So this number, which comes from that number times that number. And that number is here. Yeah, that's a 59326, 59326, 3 9s and a 2. Times that number. So these two combined should be this number, which is this number, which is these two combined. That's 7413, 6507 times 1868, 1560. So one of us can't calculate. And I was using a computer. I'll use my calculator, see where they made a mistake. 0.74136507 times 0.186815602. That 2 I didn't have, but okay. Times 0.5932612 2 is, yep, I get the same numbers they do. What? I guess it comes because I rounded this one off too soon. Did a few round off errors and then maybe, I don't know. This should be a full calculation though. Yeah, I don't know. I have no idea. But I think we have the same input numbers, so this must be a round off error somewhere. There's a delta. Delta 01 is loss function net 01. Yeah. Well, I have no idea what this is called. Ouch H1. So out of the output of the previous layer. So it's kind of the input, right? H1. We are here a little bit above the half. H1. But I think I already established this. Same thing. They put a minus here in front of it, but okay, we do out minus target. So we have the difference, out minus target, and then we repeat the out to get the derivative of the activation function, which is out times 1 minus out. And then that multiplied by one of the inputs. And the input, of course, that belongs to the current weight that you are taking the partial derivative of, which for W5 is H1. That was my conclusion as well, that this is how you can calculate it, and it seems more efficient than going through the whole shebang with all the tensors of 3 dimensions. Because it's, yeah, come on, it's just 2 multiplications and 2 subtractions. So why would we do all the tensor multiplications? Is this clickable? The delta rule? Is this clickable? The delta rule. Delta weight is alpha difference, yeah. So the alpha is the learning rate, and this dj minus y, and y is the output. So this is the loss, as it were. Well, actually the derivative of the loss function, aka just the difference compared to the target, and then the derivative of the activation function at that point, and the input. Alternatively, we have, they start over now, derivative of the loss function relative to out O1 and relative to net O1. No idea what they're talking about now. I'm going to look for what out O1 is. There's an out O1 already. It's just the output. Out O1. What are they talking about? I mean, O1 is already an output. O1 is just O1. Oh, they have split this thing in two. This is pre and post activation. Okay. Oh, okay. O1 is the neuron, the output neuron. So out O1 is the output of the output neuron, and net O1 is the input of the output neuron. I also have letters for that, but different ones. Yeah, this is just the first part of the chain rule that I just used. So everything except the multiplication with the input of the used input. That is multiplied with the current weight that we're doing here. So then you can do, if you call that delta O1, then you only have to multiply with out H1 and then you get the whole thing. Sometimes you have a minus in front of it. So to decrease the error, we then subtract this value from the current weight, optionally multiplying by some learning rate, which we will set to a half. So then the new weight is the old weight minus eta times what we just calculated, and we get that as the new weight. Some sources use alpha to represent learning rate. Yep. Others use eta. And even others use epsilon. We can repeat this process to get the new weights for W6, 7 and 8. Pertaining the output layer. To perform the actual updates in the neural network after we have the new weights leading into the hidden layer neurons. Yeah, we use the original weights, not the updated weights, when we continue the backpropagation algorithm below. I don't get that. Seems they say the opposite. Next we'll continue the backwards pass by calculating new values for W1, W2, W3 and W4. So the weights of the first layer. Big picture, here's what we need to figure out. The loss function, the derivative of the loss function relative to W1 now, which can be written as okay, this is H1 out and net. So net is the input of the... Okay, this is just H1 is now, it's not O1 but H1. This is O1, this is H1. So we go on back of course, and then we have again net is the input and out is the output of that neuron. In this case in the hidden layer. For the rest it's the same thing. Except, of course, that error is like a whole layer further. So I guess we did already calculate this one. The derivative of E total relative to out H1. That's... Did I see that before? Out. E over delta out H1. Nope. I don't think we calculated it yet. Visually, let's calculate it here. Maybe this is the trick here. So they have here a delta O1, which you just multiply with out H1 to get the difference, the partial derivative of the error function with respect to the weight that is the multiplier of that input. And then one layer back, we want maybe to get something like the derivative of E total with respect to the weight of the previous layer. For example, W1 is delta H1 times the thing that W1 is multiplied with, which would be I1. Input 1. See if that's correct, and I can find that back somewhere. Mainly looking for a delta now. There, they stop. No, this is what I was looking for, right? Yeah, that's exactly what I said. Exactly what I said. So the partial derivative of the loss function with respect to some weight of the previous layer is delta H1 times I1. That's exactly what I said. So in order to go a layer back, we need the delta values. And for the last layer, that would be the delta O1, which is just the output minus the target times the output times 1 minus the output. And then for the hidden layer, it's something else. So the question now is, how do I get delta H1? think it's this. I don't think they mentioned delta 1 before that. So the delta H1 is again out H1 times 1 minus H1. Out H1 I mean. So that's the same. But instead of output minus target, we get this. Sum over all outputs of delta O times the weight HO. What is that? Okay, I'm going to write down what I learned so far before my memory is overflowing. Now looking for delta character. Maybe not the fastest way to get it. Oh, here it is. Pretty fast. I think ChatGPT uses it differently. I also hope I then deleted that, because I didn't see the... Oh, I didn't. Well, then delete it now, because just, I don't know, I don't want to use a delta like this. Penalty, not very useful. So also, I should not talk about the bias, I think. Bias should just always be part of the weight matrix. It's way more efficient. But yeah, I don't feel like updating all this text. No, true. And then we have this delta, which I shall call. So that is something that refers to the output neurons or the layer itself. Let's call that, I don't really have the good name for that here. I'll just underscore 2, subscript 2 for second layer. And then multiplied by the inputs. Let's see, yeah, the input that belongs to that weight. Which is Z. Which Z? I guess the Z with the index that belongs. Oh, this is a matrix. That's a vector. It's a column vector Z. So the column belongs to the row of the matrix. Yep. I is the row, J is the column, and then here we use J's row of Z. So more complicated than that, right? The delta 2, just a second later, but it's also depending on other stuff. Characteristic of the second layer. Effectively, delta 2 was equal to the difference between the outputs of, oh boy, what are we talking about here? I don't know which indexes anymore, but let's begin with it's that output minus a target. damn it. Well, I don't know. It's probably I, right? Because we didn't use I yet. So that means that we have an I here as well. Just put an I here. Or both. I could put up I want to put both here, so the 2 as well, but then it looks suddenly like a 2i. Yeah. Right, so now I'm going to make a leap. So likewise, a previous layer, a previous layer's weights give us or have the gradient matrix delta. I'll just use 1 here, even though it's the layer, whatever the layer is then, that point. Just sub 1. I equals, and then we can again that, but in this case the O here is the output of that layer, but I already gave that thing a name, so that's the output, right? So that is after the activation function. And I call that for the first layer Z. Yep, Z is the output after the activation. And then in front of this we must put a sum. From here to there of, well, not of, so yeah, of something, and of something, and then multiplied, that sum is then multiplied with that thing. No, see if we can find that back. So that was this thing here over O. WHO. I'm afraid that lost me. What the hell is H here? You know, I have two indexes for my W, for my weights, but they use just one index here, which is kind of weird. So maybe the HO is just one index. Ooh. So it's like a hidden to output, I think. Yeah, this is the weight of from hidden to output. So that's the second weights. But then running over O here is not clear whatsoever. That even influences the delta? What? It comes from this summation, so maybe I understand that one. See, delta net H1 relative to W1 is probably the I1. Yeah. And this is then this. Activation function. And then this sum is that sum. Well, we know what the delta O was. I think that was written somewhere. Delta O is what? Oh, it's called delta O1. Okay. Delta sum index is E total, the DE total D out same index times out of net. So basically E total relative to net, but yeah, this is this. I'm gonna assume that they replace this with that, which it means that the WHO must be equal to that. Okay. Well, I'm saying okay, but O runs through what the fuck? This is specifically for W1. Can I see it from here? Yeah. So it's just these O's here. Mm. Maybe I'm just getting tired. My brain is slowing down. Yeah. I think I'm gonna stop because I'm not making progress here. I probably should just go buy some food because I'm too lazy to cook. Or I have to, I don't know, do something. Bring out the knights first without thinking. Because, okay, I said I would do that. It's gonna take the knight, take to the center. You invent a new opening here. How amazing is that? Yeah, you can have that if you want to. I don't care. That's all I do. Put more pressure on this pawn. But he's gonna take that. Okay, I'll do that. He's gonna take it anyway. And he undoubles my pawn anyway. That's stupid. Why give away both bishops and then resolve this problem for me? Anyways, I think I'm going to castle long, like totally. After putting another pawn in the center, maybe. Take, check. No, no more checks there. No, that's not where I wanted to go to. Let's castle long. Yeah, made a move. Wow. I was already tired, and then he started to move so slowly. Suppose you move this pawn, and he take, and I take, and he takes, and I lose a pawn. There's nothing. It's an open file. So why not? What is he going to do about it? He's going to move the pawn. Could attack the knight. Knight goes there. Nothing. Absolutely nothing. You could give check. I'm gonna go here because I'm scared for checks. I want to have my bishop on this diagonal. Difficult. Just getting out of the way of my rook. Oh, instantly I gave away pawn. I did give away a pawn, didn't I? But I can take here. It's not that bad. So we could go back here, and he takes the queen. I take the queen, he takes, and then I take here. It's not that bad. It's not that bad then. Oh, he takes that pawn. Takes that pawn. That was not what we wanted. Now I can go here though. No. Or maybe go here, and he takes. And then I take, and it's going to be inequality. Haha, he cannot take here. Where is the queen going? Let's do this. Just because. Well, the queen is going there or there. Oh, he's taking it anyway. Thank you very much. Takes it anyway. Then I take that anyway. . And then we develop the rooks. This rook and this rook. Take my pawn. I want to develop my rooks. No. Free pawn. Take it. Take it. I know you want to take it. He's defending the pawn. So lame. Lame, 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 lame. I'll just go away. And now he thinks he can do that. Maybe he can, but then again, maybe not. Let's go here, just because. And then we can block it, and then he can chase me away by putting a knight here, but not free at that square, so that would be this knight. And then, no, I just take it with this rook. Block it. Well, that pawn is lost. My friend, the pawn is lost. Okay. Now I have to defend that pawn. Still threat to take here though. And then he comes with that one. But it's pretty lame of this guy. Supposed to go all the way back? No. If I do this, he might go here. Then I just take the pawn. Yeah, I don't see a problem. No problem whatsoever. I might even just relax play this one first. Theoretically, I can just play this one and then put the rook back and then still capture there. There is nothing he can do about it. Nothing. Nothing. No. What you gonna do? Oh, what did I just do? Something in the thick up cat? Did what? That was not smart. Yeah, that was very stupid. Fuck. Let's go away. Now we are equal again. And I was winning. It's a sad day. I so want to give a check with my rook and win a pawn. Then I lose this one maybe? Oh, it doesn't let me. Do I have nothing better than draw here? Why would I be winning this? Because my king is here? No, it's not gonna happen. That's not going to happen. But attack. Is this problematic for black? I think it is. It's pretty damn problematic. I'm gonna like that. Yeah. Why I can't take. Cannot really take. I'll just go here. I can go there now. Take. Nah, let's begin with check. Keep attacking. No, I should have gone there. Shit! Gotta be fucking kidding me. Yeah. As usual, I lost. So no rematch. No, I'm going to eat. Eat. Sorry, Sonny. I didn't see that in time. Plus, I really have to go eat. That is, I have to go shopping so I can eat something. And I'm sleepy.